Log on, tune in, find out. Another good idea from Cambridge.
So thanks very much, the organizer, for inviting me to the program and give me the opportunity for this talk. So first of all, I must say that maybe my English is not so good as you could expect. So if you have questions, please speak slowly. Okay? So in this talk, I would like to speak about stable spectral shifts on K3 fibered threefold. So this is part of our work in collaboration with Bjorn Andreas and Daniel Hernandez Rupert. So for proofs and details, you can have a look into our paper. It is in International Journal of Mathematics. Okay, so the goal of the talk is to explain how we can to construct a stable bundle or a stable shift in general, shifts on three-dimensional varieties which admit a K3 fibration. And the method of the technique to do this is to use the spectral cover construction but from Fourier-Mukai transform point of view. Okay, so I will explain what that means in a while. So if you ask me about motivation for this work, I will say that aside from the mathematical importance of this object, this object has also a physical motivation. I mean, from a physical point of view, these objects are interesting because they produce solutions to the zerotic string theory. So I'm not an expert on the string theory, but roughly speaking, we can say that compactification of the zerotic string requires to produce or to construct stable bundles on a Calabi-Yau threefold whose chain classes satisfy certain conditions. So in this talk, I'm only going to speak about how to obtain stable shifts. And the problem constructing stable bundles with these chain classes is a very different problem. I'm not going to speak about this. So only how to construct a stable shift on these varieties. Well, if the Calabi-Yau admits an variation structure, a natural way to produce these bundles of these shifts is to construct them fiber-wise and then to give a appropriate global description. So first, to construct them fiber-wise, and then we have to give an appropriate global description. This technique has been used by Friedman, Morgan, and Witten to produce stable bundles on elliptic fibration in terms of spectral data. So this is the so-called spectral cover construction. Okay, so now since there are some elliptic fibration which also admit an K3 fibration structure, it's a natural question to ask if this construction also works taking into account the K3 fibration structure. So if we ask if this technique still works. So on the other hand, by using the theory of Fourier-Mukai transform, we can to reformulate the spectral cover construction given by Friedman, Morgan, and Witten. We can reformulate and we can improve it in some sense. So the idea is to use the spectral cover construction, but in terms of Fourier-Mukai transform, to obtain a spectral shift on K3 fibration. Okay? So the idea is to use the spectral cover construction in terms of Fourier-Mukai transforms to produce this kind of objects. So the plan of the talk is first I would like to give a short review of the spectral cover construction given by Friedman, Morgan, and Witten on the elliptic fibration. Second, I will try to explain how we how we can reformulate this construction in using the theory of Fourier-Mukai transform. And finally, I will explain how to use the spectral cover construction in this sense to produce a stable shift on K3 fibration. Okay, any questions? Well, so the first part is the spectral cover construction. So by definition, an elliptic vibration is a morphism between two schemes phi such that pi is proper and flat, we assume that X and B are projective varieties. And second, the fibers of pi are Gorenstein curves with arithmetic genus 1 and they are geometrically integral. So in particular, the generic fibers are elliptic curves, and singular fiber have at most one singular point. And singular fiber one singular point. So singular fiber are either a rational curve with a node or a rational curve with a cusp. And we also assume that this morphism has a section. Sigma, taking values, I mean, such that it doesn't mean the singular point of the fibers. Okay, so the idea of the the idea of the spectral cover construction given by Friedman, Morgan, and Witten is the following. We consider V and stable, a vector bundle on X such that the restriction to every fiber is semi-stable, regular, and with trivial determinant. Okay, so Vt denotes if T is a point of B, you take the fiber xt, and Vt is just the restriction of the fiber. So by definition, this vector bundle defines a morphism between B and M, where M is a relative moduli space parameterizing this kind of object. Okay? Now we take here the universal spectral cover of M. And we consider the pullback of this section by alpha. So this pullback is a closed subskin of X, which is a flat covering of B of degree n. N is the rank of the vector bundle. So Friedman, Morgan, and Witten prove that there is a unique Lie bundle on this cover. There is a unique Lie bundle L on CV such that V is isomorphic to Px star Pc star L times P bar, where we have here the fiber product. Px and Pc are the natural projection. And P bar is a vector bundle here, parameterizing the Jordan-Holder fit factors of the restriction of B to the fiber. Okay, so more or less is the restriction of the Poincare shift to this fiber, to this product. So Friedman, Morgan, and Witten prove that we say that V is a spectral bundle, and the pair C and L is the spectral data corresponding to V. So Friedman, Morgan, and Witten prove that there is a one-to-one correspondence between this object and this object. So they prove that there is a one-to-one correspondence between spectral bundles and spectral data. Okay, a spectral bundle means a bundle such that the restriction to every fiber is semi-stable, regular, and with trivial determinant. And spectral data means a covering of B and a light bundle on the cover. So this is a theorem. Moreover, they also study the stability of these spectral bundles, and they get that if we fix H and HB polarization on X and B, polarization means an ample divisor, then, or given V, there exists a non-negative integer which depends on V. This is very important, such that V is stable with respect to H plus M P star HB for all M bigger or equal to M0 if the spectral cover is reduced and irreducible. Okay, so using this construction, they can prove that we can construct a stable spectral bundle on an elliptic fibration. But since these bounds depend on the sheaf, we cannot use this construction to give isomorphism between the moduli spaces. So the question is if we can find an effective estimation for M0. So the question is, where effective means depending only on invariance. So in general, the answer is no. So the answer in general we don't know, or we don't know yet. In particular, Friedman, Morgan, and Witten prove that we can find an effective estimation in the case of elliptic surfaces, and if the dimension of the base is bigger than 1, there is an effective estimation for rank 2 spectral band. But in a more general situation, we cannot give a positive answer. Okay. So the second part is to explain the spectral cover construction by means of Green-Bouquet transform. So we take again x over b, an elliptic fibration, and now we consider the Allman Kleinman compactification of the relative Jacobian of x. So this is a fine moduli space parametrizing torsion free shift on the fibers with rank 1 and degree 0. So since x hat is a fine modular space, there exists a universal family. Moreover, we have here a section, and this section induces an isomorphism between x and x hat. This isomorphism is, you take here a point, and the image is the ideal shift of x times this light band with T is the image of the point. Okay, so this is a light bundle because we are assuming the section doesn't meet singular points of the fiber. But if you take a singular point, this is only torsion free, but it's not locally free. So we have to consider the compactification of the relative Jacobian and so on. So using this isomorphism, the universal family can be seen as a shift on x times x over v, and which can be normalized such that P is isomorphic to I delta tensor where P1 and P2 are the natural projection of the fiber product into the factors. I delta is the ideal shift of the relative diagonal. And omega is the push forward of the relative varying shift of pi, and rho is the composition of one projection and the elliptic fibration. So now is a well-known result that the integral factor whose kernel is this object is an equivalence of the derived category of x. So the integral factor given by P is an autoequivalence of the derived category of x. So by definition, you take here a complex, you consider the pullback by the first projection, then you take the tensor by P, and then you take the push forward by the second projection. Okay. Moreover, if we denote by phi hat the integral factor whose kernel is P star times P1 star omega xb, we know that this is a Fourier-Mukai transfer as well, so this is an equivalence, and this is the quasi-inverse of the first one, the quasi-inverse up to sieve. I mean, you take the composition, you have here the sieve by -1. So now the idea is to use this Fourier-Mukai transform to reformulate the correspondence given by Friedman-Morgan-Witten between stable sieves and stable data. So the idea is to take E, a relative torsion free sieve, torsion free mu semi-stable sieve on X, with rank n and degree 0. And now for every point T on the base, we consider the restriction of E to the fiber. So using the theory of Fourier-Mukai transform, we know that the Fourier-Mukai transform of this object is a complex concentrate on degree 1. So we know that the Fourier-Mukai transform of this object is isomorphic to sieve Et hat up to sieve. Here phi t denotes the integral factor whose kernel is the restriction of P to the fiber. And moreover, using this theory, we know that Et hat is supported on points. The idea to do this is that we know the description of moduli spaces of semi-stable sieve on the fibers. I mean, if you have xt a fiber, we know that the moduli space of semi-stable sieve on the fiber X is isomorphic to the symmetric product of the fiber. This is the moduli space of semi-stable sieve with degree 0 and rank n. So here the correspondence is you take a point here, so this is equivalent to a direct sum of torsion free sieve. And now you take the point corresponding to this object in the Jacobian. Okay, so actually you have take here the Jacobian, but this is isomorphic to the fiber using this isomorphism. So here you have So, we have this situation, a relative torsion-free semi-stable sheaf with rank n and degree 0. So the Fourier-Mulcahy transform of the restriction is a sheaf up to shift, and this sheaf is supported on point. So now we define, well, using again the theory of Fourier-Mulcahy transform, we can say that this is a sheaf E hat, a flat sheaf on X such that the Fourier-Mulcahy transform of E is isomorphic to E hat up to C. And we define the spectral cover of E as the modified support of E hat. So this is a closed subscheme of X, which is a flat cover of the base of degree n. So the idea is you have the vibration here, and here you have the dual vibration. So you take a fiber here, you consider the restriction of E to the fiber, you transform, and you obtain here a sheaf supported on points on the fiber. So by flatness, if you move along the fiber, you obtain the spectral cover. So this is the reason because we have to consider the modified support instead of the ordinary support, because the format is compatible by base chain and the usual support maybe not. Okay.
The push forward of the dualizing sheaf of X with respect to B to P, was it like, why is it trivially?
The push forward of what?
Is rank 1?
What do you call omega?
What does
Omega means the push forward by P of this.
So what is it? Is it the sheaf?
Is it the rank 1 engine?
It has rank 1, yes. Because the fiber are elliptic curve. I mean, in the fiber, the restriction to the fiber of this is the structural sheaf of the fiber. Okay. And we define L as the restriction of E hat to the spectral cover. So this is a pure sheaf on X of dimension equal to dimension of the base and with rank 1. So now to do the construction in the other way, we use the other Fourier-Mulcahy transform. So here we take C and a flat cover of B of degree n, and we take L as if like this. So the push forward by the immersion define a sheaf on X supported such that the restriction to every fiber is supported on points. So we have here the spectral cover, we take L. So if you restrict to any fiber, this shift is supported only on points. So now using the theory of rhythmic transform, we can say that the image of E is just a shift. And this is a spectral shift corresponding to the spectral data C and L. Moreover, we can prove that E hat is a relative torsion free shift, semi-stable, with degree 0 and rank. Okay, so using phi and phi hat, we can give we can reformulate the correspondence given by Friedman-Mokanowitz. We can reformulate the correspondence, and we can improve it, because here we don't assume that the spectral cover. Wait for the stability. We know that E hat is, we know that there is M0 depending on E hat, such that E hat is mu stable with respect to H plus N for all n bigger or equal to n0, if and only if L is mu stable on C with respect to the restriction of this polarization to the curve, or to the spectral cover. So in this sense, we improve this method improves the original construction, because we don't need to assume that the spectral cover is reduced and irreducible. And moreover, we obtain a larger class of spectral bundles. In particular, if the spectral cover does not meet singular point of the fiber, the spectral shift corresponding to this spectral data is a bundle. And of course, if we assume C irreducible and reduce, then L is always mu stable on C. So the spectral bundle corresponding to this spectral data is stable, like in the construction of Friedman-Mokanowitz. But here we have the same problem, that this M0 depends on the shift, and in general it doesn't depend on invariance. So finally, I would like to explain this construction in my case. So the case of K3 fibration. So for us, K3 fibration means a morphism B between X and B, such that P is proper and flat. X and V are smooth and projective. B is an irreducible curve. And the generic fiber is a K3 surface. That is, the lysine sieve is trivial, and H1 is 0. So in this case, the role of the dual vibration is played by certain relative moduli space. So we have a relative modulus. If you fix a polarization X on H on X, we have a relative modulus space of a stable sieve on the vibration. So that means close points here are a stable sieve on some fiber. And if you take here a point, the fiber is the stable the moduli space of a stable sieve on the fiber. And now we consider an irreducible component of here. Such that Y is fine and projective. The dimension of Y is 3, and the morphism between Y and V is equidimensional. So under this assumption, Bridgeland and Machocha proved that we are assuming that Y is fine, so this is a universal family. So Bridgeland and Machocha proved that the integral factor given by this universal family is a Fourier-Mukai transform. Moreover, they prove that Y is a K3 vibration, and if X is Calabi-Yau, then Y is Calabi-Yau as well. So now the idea to produce a stable shift on X is the following. This is the spectral construction. We consider C and reduce curve on X on Y. Such that C is a flat cover of B of degree n. Then we take L, a line bundle on C. So as in the case of the elliptic vibration, the push forward of this line bundle define a shift on X, on Y, such that the restriction to every fiber is supported on points. Then again, using the theory of Fourier-Mukai transform, we can prove that there exists a shift, a flat shift on X such that the Fourier-Mukai transform of E is E hat. So C and L are the spectral data, and E hat is our spectral shift. Now it's easy to prove that the restriction of this guy to generic fiber is isomorphic to this decomposition. Where y1 dot yn, y1, yn are the intersection between the cover with the fiber, IT. And by py, I'm denoting the stable shift corresponding to this point. Okay. But in general, we don't have this decomposition, but we have that E hat T has a filtration whose factors are isomorphic to this guy. So using this, we can prove that E hat. This implies that E hat is torsion free. It's a torsion free shift. And the restriction of E hat to every fiber is mu semi-stable. So now we're using this fact, we can prove that these spectral shifts are mu stable. So we have theorem. So the C's are non-negative integer numbers, again depending on E hat, such that E hat is mu stable with respect to H plus M F. F is the generic fiber. For all m bigger or equal to m. So, and the idea of the proof, if by definition we have to prove that the slope of Hm of E hat is smaller or is smaller than the slope with respect to Hm of G for all quotient G for all torsion-free quotient. So now, if you compute these slopes, this inequality is equivalent to say that the slope of E with respect to H minus the slope of E hat plus 2m is smaller than 0. Here the subscript denotes the restriction to the generic fiber. So this part is smaller or equal to 0, or if it is bigger than 1, this part is bounded when you move this quotient. Okay, but this is by the system of the minimal stabilizing shift. So this part is bounded. And here we know that E hat T is mu semi-stable. So this part is always smaller or equal to 0. So the question is, if we prove that this part is strictly smaller than 0, we have the inequality, taking m bigger in that. And sorry, I forgot to put the hypothesis. If C is reduced and irreducible. So using this condition, you can prove that this is strictly smaller than 0. Okay. So again, there is a question, and the question is if we can find an effective estimation for M0, and the answer is yes in this situation. So to do this, I have to recall a definition. Given f as if on X, the discriminant of f, discriminant is the class is this class, and Bogomolov's inequality says that if f is mu semi-stable, then the discriminant of f times h is bigger or equal to 0. I mean, Bogomolov say. H, then so now using the Bogomolov inequality and a technical lemma, we can prove that. Sorry?
You forgot the inequality.
Inequality.
It's less than or equal.
E.
No.
It's majority one.
Sorry. So let me write the lemma. Not important. So we fix H0 and I smooth polarization on X. So we have late dB and a divisor on x and k an integer number such that 0 is bigger than the square h0 and this is bigger or equal to minus k, then either the h0f is equal to 0 or the h is bigger than 0, for every m bigger or equal to okay, so this is a technical lemma. So using this lemma, the Bogomolov inequality and the definition of stability in the sense of Miyaoka, we can prove that our spectral shift E hat is mu stable with respect to hm, that means h0 plus mf for all m bigger or equal to rank r square n square. And this bounded only depends on invariant, topological invariance. Okay, so this allows us to produce isomorphism between this kind of object and another model spaces. Okay. Okay, so I think I stop here.
Questions?
Yes.
So you said you wanted stable bundles with specific Chern classes.
The idea is to obtain the stable bundle with, in the sense of the theoretic string theory, you need to obtain a stable bundle with C1 equal to 0 and C1 of the spectral bundle minus C2 of the variety effective class, and another condition about C3. But with this condition, it's not easy to obtain this invariant. So now the idea is, well, you have a stable shift, and for instance, you study extension of this spectral shift. Of you take an spectral shift and you twist it by a line bundle or something like that.
Questions? Thanks, Nathan, again.